In SUINK, the solutions are validated using 3 automotive use cases. First, we developed temperature sensors integrated in the car seat for smart heating. Second, we are integrating a temperature and humidity sensor in a polymeric bracket. And third, we have a strain sensor integrated in the fiber composite to monitor the structural health of this composite.
Santexbal is a textile research center, so we are in charge of the textile demonstrator. In the SUINK project, this is a composite seat shell for the car. So a car seat is composed of a self-reinforced composite. In fact, PLA itself is a very brittle polymer, but we use techniques to combine different grades of PLA to reinforce the seat shell while still using one component being PLA. This gives you the advantage that it's a monomaterial that is easy to recycle, and in the meantime we can also integrate electronics and so on in the car seat shell. In SUINK, this is a cantilever, so a component that moves, and from the movement we recuperate the energy. We collect this through energy harvesters into a collecting system, and then we use it to power local sensors like a humidity sensor and a temperature sensor that is present in the car seat. We developed a small-scale demonstrator where we can see there is a moving part in the car seat shell. So we will see if we press the cantilever that a voltage is created, and this small energy we store in a local energy storage unit, and then we try to use it to power a small temperature sensor and humidity sensor.
Due to modern safety and comfort standards, windshield electronics are getting more complex, holding more sensors and more cameras. Oriva's role in the SUINK project involves redesigning the whole electronics so these sensors can be powered up more efficiently and with fewer cables. The main advantages in terms of sustainability and environmental impact of our solution is that we have designed the whole system with the SUINK developed technologies from scratch. We have integrated the whole system in a compact package, so we require less cabling and less systems overall, reducing the whole impact and the carbon footprint of our solution.
The strain sensors are co-developed by CRF and GenMate in order to design a system that can be integrated into a structural, semi-structural component and combined with the self-charging power system developed during the SUINK project. This kind of strain sensor will be able to monitoring stiffening. In other words, we can monitor the state of health of our components well before a critical failure occurs. The adoption of the SUINK systems can enable us to properly design in an optimized way such components using less raw material, optimizing the weight of the components, and so reducing the general environmental impact of such components. The strain sensor coupled with the self-charging power system will enable a repair strategy. For example, we can identify repair a damaged area instead of replacing the full component. This will introduce clear advantages in terms of raw material usage, energy consumption, and resource depletion.
FTMC joined SUINK consortium with proprietary SSL technology. Key aspect of it that it allows to form conductive tracks in practically every type of not conductive material. So applying our technologies, we introduced laser-induced graphene to use it instead of commercial piezoresistive sensor, and furthermore we added our before mentioned SSL technology to seamlessly combine this laser-induced graphene and copper metal interface. We made this demonstrator integrating all the circuits, the active sensor, and other side you can see the controller with the communication unit. So such controller can be used in automotive industry. It has such advantages that it's low profile, so it can be easily integrated in any part of car.